look at and see the problem we did last time was not good enough for this problem. Was there an issue? You see, this was a problem that we did in class. And this is the same thing with minor changes. We're going to work on it. I just wanted to understand, was it a more difficult situation, or?
I wouldn't say it was that difficult, but I ended up getting x squared plus 2x equals 24. And I simplified x squared. I was just curious if I did that. I wasn't
of course.
sure.
Okay, absolutely. Anytime, any problem. I just wanted to understand what was different. Okay, so first of all, I will say that x plus 2 has to be greater than 0. And of course, for this one, so this is greater than -2, and this is greater than 0. So if you overlap them, then you will see the domain is 0 to infinity. So at the end of the day, whatever I get, if it's not a number between 0 and infinity, it cannot be accepted. Is this okay so far for everyone? Okay, perfect. So now I have to condense. Do not state the domain after you condense. That would be a terrible mistake. The domain has to be stated on the raw equation. Always. Don't touch anything. State the domain, and then you can do whatever you want, because the domain will change. If you try to state the domain after you condense, the domain may be different. So the domain will always be stated on the raw equation or the raw function. And now I can just rewrite it as x squared plus 2x equals natural log of 24. And then x squared plus 2x equals 24. This is quadratic. I have to set it equal to 0. It's the only way. So x squared plus 2x and then minus 24. And then we have to factor. If you have difficulties factoring, we cannot go back to factoring anymore. So you can use the calculator and simply factor into x plus 6 and x minus 4. And we get x equals -6 and x equals 4. I will say absolutely not, and this is okay. Is this okay? Perfect. Anything else? Other questions? Anybody? Is there anything else we need to go back to? Other problems, homework or otherwise? Pearson, anything you want.
Can we do 18 from the homework?
Yes, 18 from page, or the solutions will be posted, but I would like to go over the problem that you need. 18, I don't know. I haven't written solutions yet. So when you say 18, you mean from 210?
I think it's 205. Let me check the page number. Yeah, it's from 210.
From 210?
Yes.
Okay, perfect. So we have y equals x, e to -2x, plus e to -x, plus x to the third, and we're asked to differentiate. When we're asked to differentiate, we're only asked to write y prime. This is a product. The first function prime is 1, e to -2x plus x times e to -2x times the inner function prime. Now I'm here, plus e to -x times the inner function prime. And now I'm here, and this is plus 3x squared. And yes, I will rearrange it a little bit. So there is nothing I can do. I just want to get rid of these parentheses. So e to -2x, then minus 2x e to -2x minus e to -x plus 3x squared. And there is nothing else we can do here. It has to stay as is. Good?
Would it be okay if we also change the e minus 2x into fractions, the numerator?
So you can if you want to as 1 over e to 2x.
Yeah.
Yeah, that's fine. Good. Is there anything else we need to go back to?
Could we go over problem 54 on page 211?
211, 54. Yes. So let's take a look. I also hope that you will always go back to the solutions that I post when I start grading, right? Please, always do that. So we have the concentration, because we did 53. That's the reason why we did 53, because this is the same problem. So we have C of t equals 250 e to negative 0.03 t. And they're asking us to, so this is in ppm, parts per million, and t is in minutes. Very important, because without measurement unit, there is a problem. Find the concentration after 1, 5, and 12. So do we need to do that part, to plug it in? Okay, we'll do that. In part B, they're asking us to graph it on 0 to 20. And in part C, so I'm going to also add here 8. And also they want C prime of 8 as well. So like we did last time, I'm going to determine both C and C prime of t. So all you have to do is just plug it in. So let's plug it in the graphing calculator. Please don't do this one by one. That would be terrible. Okay, so 250 e to power negative 0.03 t, and close. And now let's also calculate the derivative. So C prime of t is 250 times e to negative 0.03 t times the inner function prime. Okay, so this is negative 3 times 25 is 75, and I have 2 decimal digits. So it's 7.5 e to negative 0.03 t. Am I correct? Yes. Good, so I'm going to enter the derivative as well as negative 7.5 e raised to the same thing, of course, negative 0.03 t. Oh, that's not what I meant. Oh, it added. Good, that's awesome. So now I go to second and table, and I have 1, 5, 8, and 12. 1, 5, 8, and 12. So the first one is 242.61. The next one, negative 7.28. Then for 5, 215.18. And then negative 6.446. And then for 8, that they're asking anyway, 196.66. And negative 5.9. And finally for 12, 174.42. We were not asked to determine the derivative for all of them, but I just wanted to see what's going on here. Good. So then they were asking us to graph the function from 0 to 20. So I will just simply de-highlight this. I don't want to graph the derivative, so I only want to graph the function. So I go to Windows, and it's 0 to 20. I'm going to put a scale of 4. And how high? So it goes from 0 to 250 with a scale of 50. Good. So now when I hit graph, really? What's the problem? Is the window the problem? Yes, of course the window is the problem. Because I want 0 here, I want 250 here, and I want 50 here. Yes, they were correct. Good. So here's the graph between 0 and 20. And we see that 242 roughly at 1, and then it continues decreasing. And at 12, it reaches 174. Okay. So what was the issue on this problem, you think? What was it missing? We haven't written the final part C, but what was the problem here? You just wanted to see the numbers, or was it something missing, or?
Yeah, I just wanted to double check to make sure I did it correctly.
Sure, but also remember to look at the solutions, always. Okay, perfect. So now we're asked to interpret these. And here's the interpretation. 8 minutes, because T is in minutes. 8 minutes after an intervention, the concentration of the medication in the bloodstream 8 minutes later, after we take the medication, is 196.66 watt parts per minute. Parts per million, sorry. ppm, parts per million. Now, how fast and in which direction is the concentration changing in the bloodstream 8 minutes after we take the medication? It's decreasing. The concentration after 8 minutes after we take the medication, it's decreasing at the rate of 5.9 parts per million per minute. So this is ppm per minute, and this one is only ppm. The measurement unit is crucial. Please understand that. Absolutely crucial. Good. Anything else? Are there other questions? Anything else? Do we understand the difference? Because this is very important. Yes? Okay. Can we continue then? Is there anything else you'd like to go back to? Anybody? Okay, in that case, we're going to try to finish chapter 2 because we only look at 3 sections with 2.3. And in 2.3, finally, we talk about derivatives of natural log functions. Only the natural log. There are other options, right? We have log x, which is base 10. We have log base 3 of x, and so on and so forth. For some reason, again, the book only presents this. So if you want, I can show you the formulas for anything else or any other base, but it will not be, for some reason, part of what we're going to do here. It's up to you. Good. So when we differentiate natural log, we get 1 over x. Of course, times the inner function prime, but that is 1. If we have natural log of a function prime, can anyone discover this formula for us? Help us with this? It's okay if you're wrong. I'm assuming you have not seen it before. So can anyone give us the derivative of natural log of a function? The idea is always the same. Anyone would like to try, please?
Would it be 1 over the function times the function prime?
Of course. exactly as we always did. Perfect. This is it. I want to draw your attention to something. And this comes in later in chapter 4. But I just want to discuss it now because it's in this section. If anybody remembers the definition, the formal definition of the absolute value, this is all from algebra. This piece is from algebra. We haven't really discussed this before. Anybody remembers what is the absolute value of x? What does it equal to? Well, it's x if x is greater or equal to 0, or negative x if x is less than 0. So if we are given x as being 5, we know the absolute value is 5. If we're given x as being negative 10, we know the absolute value of negative 10 is 10. But what if we don't have the values? What can happen? That's what the formal definition is. So the absolute value of whatever is whatever if it's positive. But it's the opposite of whatever if it's negative. That's all this means. And the question is, and again, as I said, it will come up in chapter 4 when we talk about something else. When we differentiate natural log of x, what is natural log of absolute value of x, I meant to say? What is it? Well, it's this. What is it? It's the natural log x if x is positive. Notice that I cannot plug in 0 here. And is natural log of negative x if x is less than 0. So let's come back for a moment. That's in general, the absolute value of x converts into x if x is positive, of course, or 0. The absolute value of x can be changed into negative x when x is negative. So the answer is always positive, in other words. If it's positive, it's just itself. If it's negative, just put a minus in front. Okay, what are we doing with this? Well, we just want to show what happens when we apply the natural log, to the absolute value of x, and then we differentiate. So if I apply here natural log, I have to apply here natural log, and I have to apply here natural log. That's all I did. Just copied it. Now I would like to differentiate this piece. But differentiating this piece means differentiate these two. So when we differentiate the first one, there is no problem. It's 1 over x for x greater than 0. But when we differentiate this piece, I have to use the chain rule, because this is no longer a plain x. It's negative x. So what do I get? I get 1 over negative x times the inner function prime. But when you simplify this, you get back 1 over x. So what, in general, what am I really saying? I'm saying that natural log of the absolute value prime, it's still 1 over x. In order for you to understand this, I had to start with the absolute value. I had to apply natural log to the absolute value, and then I had to show what happens when we differentiate natural log based on the chain rule. So we're going to come back to this specific idea in chapter 4. Okay? So now that's all we needed to look at. Let's open on page 216 and just work on some problems here so we can move on. Okay, so let's differentiate a log function from 1 through 19. Let's find an equation of the tangent line, which is very important. We've been looking at this all over for all functions, on and on and on and on. So if you don't mind, I will